Next, we'll discuss how to solve first-order linear differential equations. And all linear differential equations look like this. And the goal is to solve it. That is, we want to find some unknown function y that satisfies this equation. And to solve it, so here's the strategy. The strategy is to turn the left-hand side into the derivative of some product. So we're going to have some function here that are multiplied by one another, and then we have a derivative on the right, derivative taken of all of it. And on the right side, we're going to have, well, whatever we end up having. So this is kind of the pattern that we explored previously. And now the question is, can we always do this? And the answer is yes. So the idea is that now that we know what the goal is, we're going to strategically pick some function which we'll label mu of x, and it will be called integrating factor, such that when the entire equation is multiplied by this integrating factor, so that the integrating factor now becomes the leading coefficient of this equation, and then it is now present in every coefficient of this equation, so as on the right hand side of the equation. So the goal is to find such integrating factor that the left hand side of this equation is now the derivative of some product. And we know that it is possible to make it so that it's a derivative of the product of the integrating factor and the function itself. And in order for that to happen, so again, if we just work backwards now, if we take the derivative of this product using the product rule, we're going to have, according to the product rule, mu of x times y prime plus mu prime of x times y. So notice how we can totally achieve that, because look, we want this to be equal to this, and it is totally achievable if mu prime of x, which is here, is equal to this coefficient right there. And if you carefully look at this statement, this is actually a differential equation, and if you look more carefully, you will be able to notice that this is actually a separable differential equation, and we definitely know how to solve all separable differential equations. So to solve this differential equation, we're going to separate the mu and the p. So on the left side, we're going to have d mu, and we're going to divide everything by mu. And on the right side, we're going to have just p, and we're going to put dx over here, and we integrate this, so we're going to end up with ln of absolute value of mu is equal to and we don't know what it's equal to unless we know what p is, so we can just write it like this for it now, and we of course going to have some constant of integration there, which still inside of the indefinite integral. We don't need to write it yet, but from here we can find mu by exponentiating And yes, we can put the absolute value here, and it will be true for either regardless of whether mu is positive or negative. So let's just, for simplicity, remember we're only looking for one such mu, so let's just drop the absolute value here, and as a result we have what appears to be a formula for determining integrating factor. And this is the integrating factor that we strategically pick, and it will always be the case that after you multiply both sides of the equation by the integrating factor, you will have on the left hand side the derivative of the product of mu by the unknown function, and on the right side we're going to have just the product of q and mu of x. And when you get this far, so after you rewrite the original differential equation in this form, we can continue the process of solving this differential equation by taking the derivative of both sides. Taking the integral of both sides, and by doing so we obtain the solution in implicit form. So the last step that we would have to do is divide both sides by mu of x. So again, remember, part of this indefinite integral will be some constant of integration, and then all of this will divide by the integrating factor to obtain the general solution in explicit form. So it appears that we found a way to solve first order linear differential equation. Step 1, find the integrating factor. Step 2, multiply both sides by the integrating factor and rewrite the left hand side as the derivative of a product. And then step 3, we integrate the right hand side and then isolate the y to produce the general solution in explicit form. And then, if necessary, if the initial value is given, we can use it to find the value of c that solves the initial value problem. So this is going to be our way of solving first order linear differential equations. And next we do a few examples. So here's the first example. Let's solve this differential equation, and here let's assume that x is positive, and it's definitely not equal to 0 because x is in the denominator. And how do we know this is a linear first order differential equation? Because we can identify the p, which is 1 over x, and q, which is 2, which make this equation written in this form. Now that we know it's the first order linear differential equation, we're going to solve it by following these steps. First, we're going to find the integrating factor using this formula. So, step 1, we're going to find mu. and we integrate 1 over x. It's in the exponent, so it's going to be ln of absolute value of x. But remember, x is positive, so we can just drop the absolute value and write this whole thing as e to the ln x, and then e and ln can be cancelled. So when x is in the domain of ln, so which it is. So the integrating factor is x. In step 2, we're going to multiply both sides by the integrating factor. And if everything is done right up until now, the left-hand side should become the integrating factor times the original unknown function, and all that taking the derivative of. So it's always going to be the case, so you can count on that, and if it's not true, then something is wrong. And we integrate both sides, or we find the unknown function on the left, the derivative of which is given on the right by integrating the right-hand side. And the last step for us is to, I guess we're already doing step 3 here. So the last part of step 3 is to isolate the function by dividing everything by x, which was the integrating factor. So the final answer is this. This is the solution of this first order linear differential equation. Let's do another example. Let's make this the initial value problem. And again, let's identify p and q values that tell us that this is a first order linear differential equation. It is linear because p is equal to -2 and q is equal to 4x plus 3. So that we have exactly this form of a differential equation, which is what we call first order linear. And step 1 is to find the integrating factor using this formula. In our case, it will be integral of -2 dx, so it's going to be e to the -2x. And again, we don't need plus c here because we only need one such function to be able to continue with the solution. So we just make c equal 0, and we continue by multiplying everything by e to the -2x, which is the integrating factor that we found. And if everything is done correctly, the left-hand side should become the derivative of the product of the integrating factor and the original unknown function. You can double check that if you'd like, but I think we haven't made any mistakes here yet, so I'm 100% sure that this is true. And we go into step 3, where we find the function inside of the parentheses here by integrating the right hand side. So e to the -2x times y is equal to the integral of 4x plus 3 times e to the -2x dx. And here we now have an integral question, which we should be able to find I don't want to say easily, but by now we definitely know how to integrate all functions. So let's hit a pause button here on solving differential equation, and let's take this problem and let's make sure we know how to find this integral by hand. Of course, in real life you can just use technology, but if technology was available, we probably would have used the same technology to solve the original differential equation. So it only makes sense to do all of this by hand to practice this skill. And how do we solve this problem? I'm going to do this by parts. I'm going to choose my u to be 4x plus 3, then du will be 4 dx, and dv is e to the negative 2x dx, thus v is negative 1/2 e to the negative 2x. And we're going to plug it in into this integration by parts formula, uv minus integral v du. So we get 4x plus 3 negative 1/2 e to the negative 2x minus integral v, which is negative 1/2 e to the negative 2x, du, which is 4 dx. And I'm just going to simplify it a little, maybe rearrange some coefficients, and I'm going to take out the 4 and negative 1/2 out, so it's going to be plus 2 integral of e to the negative 2x dx, but we literally just computed this integral earlier, so we know exactly what that answer would be. So let me just erase this, and I will write the answer instead. So we're going to have negative 1/2 e to the negative 2x, and we're going to have of course plus c over here. So again, let me simplify everything once again. So we have negative 1/2 4x plus 3 e to the negative 2x minus e to the power 2x plus c. We can simplify it further by distributing the expression here, actually. So we're going to have negative 1/2 times 4x, so it's negative 2x e to the negative 2x. And we're going to have negative 3/2 e to the negative 2x. So combining the like terms now gives us the final answer. So negative 2x e to the negative 2x minus 5/2 e to the negative 2x plus c. So this is the solution, not the solution yet, but this is what the integral on the right hand side is equal to. We can take that integral and plug it in right over here. So this integral is equal to negative 2x e to the power negative 2x minus 5/2 e to the negative 2x plus c. And remember, the last step is to isolate the y, so we multiply both sides by the reciprocal of e to the negative 2x, which is e to the 2x, and our final answer for the general solution looks like this. However, remember, we had the initial value. So we have initial value problem here, and to solve the initial value problem we have to determine the value of c that makes that condition, that satisfies that condition. So we're going to plug in 0 for y, for x, and we're going to get on the left side -2. Here we have 0. And solving for c gives us what? So -2, it seems like it's 1/2. And therefore our final solution is all right. Let's do one more example. And this time we're going to solve this differential equation. And first we're going to have to make sure that it is first order linear differential equation. And it is linear. How do we know it is linear? We're going to write it in the form y prime plus py equals q, and for that we're going to have to divide everything by x ln x. And we identify p to be 1 over x ln x and q to be e to the x over ln x. And if it's linear, we can solve it by first finding the integrating factor. So the integrating factor is the e raised to the power, the integral of p, and p is 1 over x ln x dx. And again, we are so far in the course that we do know how to integrate any function, and to do this integral we're going to do a quick substitution. T is equal to ln x, and then dt is 1 over x dx. So this integral now becomes integral of 1 over t dt, and it is ln of absolute value of t plus c, but remember t is ln x, so we have ln of absolute value of ln of x plus c. Again, we're looking for the integrating factor, so it will work exactly the same way for any value of c, so might as well set it equal to 0, and then e raised to the power ln of ln x gives us the absolute value of ln of x. And since x is greater than e, that makes ln of x positive, so we can absolutely we can get rid of the absolute values. So this is our integrating factor. So in step 2, we're going to multiply everything by ln x. So ln x times y prime plus 1 over x y is equal to e to the x. So now the equation doesn't look as intimidating as it used to. And if we did everything correctly, on the left hand side we're going to have the derivative of the product of the integrating factor and the unknown function y. And now in step 3 we're going to find what's inside of the parentheses by integrating the right hand side. And I lost... no, actually I didn't lose anything. So we have integral of e to the x dx, which is, everybody should know this integral. It's just e to the x plus c, and we finally isolate the y by dividing everything by the integrating factor, and the final answer can be written, I don't know which of these two expressions is simpler, but both of them give us the general solution of this differential equation. So this is how we solve first order linear differential equations. Again, step 1, we find the integrating factor. Step 2, we multiply by the integrating factor and rewrite the left hand side as the derivative of the product of an integrating factor and the unknown function. And in step 3, we integrate the right hand side and isolate the y. And if necessary, we use the initial condition to solve for the constant c that makes it that satisfies that creates the solution that satisfies the initial condition.